it's good practice. So let's say that you've got aluminum and you've got oxygen in a molecule. So there's aluminum and there's oxygen. But we don't know how much aluminum and we don't know how much oxygen. Right? But we do know that 52.9% of this molecule, you okay?
Yeah.
52.9% is aluminum. So now we know a lot. We can actually solve this problem. That's all we need. That's why I like these problems, because they have such a small starting point. I know. Isn't it great?
Yeah.
Yeah. Okay, so I know you're not being sarcastic, right?
I'm not being sarcastic.
Awesome.
I actually do love it.
So what's the rest of this oxygen?
Like 40.
Oh, it's a
47.1.
Yeah, 47.1% is oxygen. So now we can make this really easy on ourselves and just suppose that there's this substance, we've got 100 grams of it. Okay, so if we do that, then we can just change this into grams. 100 grams of this, 100 grams of that. So now, since it's a percent, we can just change those into grams pretty easily. If we assume that we're dealing with a molecule that is 100 grams. So now, all we have to do is turn these into turn these into moles, and then from moles, you can see the ratio of the moles to each other. Pretty easy. So now I'm going to do that. I'm going to take this aluminum, and I'm going to turn it into moles of aluminum. What's a mole of aluminum? How much does that weigh?
Aluminum is 26.92.
26.92?
Yeah.
Thank you. Grams. And that'll give us a certain amount of moles.
1.9605663.
Okay, I'm just going to go right there.
I read it all.
That's great. I'm just going to leave it right there, though. Okay, that's great. 1 mole of oxygen now. I'm down at the bottom. I'm going to turn this into moles as well. So this is going to be something else. It's 4.71 divided by 15.999. What's this going to be? It should be 2 point something.
2.942.
942. Okay, that's good enough. So this is moles of O, and that's moles of AL. Which one's smaller? The black or the blue?
Black.
Black. Good. Smaller. So now, if we're going to relate this to this and see what the ratio is between these moles, we simply divide by the lowest amount of moles. So this is going to be divided by 1.96056. Okay? This is obviously going to be 1 because this over this is the same. It's going to be 1. We've got 2.942 divided by this. It's going to be something like
Equals 1.5.
1.5.
There's something else.
There's more decimals.
Times 2.
1.5 and then any other decimals?
It's 1.50. 1.
Okay.
5.
1. Okay. So this is 1.5. This should start ringing bells in your head.
Multiplied by 2.
Yes! At this point, if this ratio turns out to be 0.5, then you're going to multiply everything by 2. I'll give this to you on the test. If it's 0.5, then you multiply by 2. If it's 0.333 repeating, then you multiply by
Oh, but you're giving that
3. I'm going to give this to you. Yes, because I'm nice. And then we got 0.25. That's going to be multiplied by
4.
4. Good. And the other way, above the 5, it's 0.667. It's going to be multiplied by 3. And over here, 0.75. That's going to be multiplied by 4. Okay. These are the key numbers that should just start ringing bells in your head. When this is not just a perfect ratio, it should be a perfect ratio. It should be just like, it should be exactly 1, or it should be exactly 2.00. It could be 2.001, or it could be 1.9998, right? You could be doing all that stuff. But if it gets to be 1.5, or if it gets to be 1.25, or maybe 3.25, or whatever it is, if it gets really close to these magic numbers right here, that's when you start dividing, that's when you start multiplying by these. So you can get whole number ratios.
But if you get like 1.99, you can just round it, right?
Yeah, 1.999. Now this is dangerously close to that point where you're saying, oh, that'll do. That's okay. And you'll notice the final ratio is just 2 to 3. Okay, because if you multiply this, both of these by 2, multiply this by 2, this is going to equal 2, and this is going to equal 3. So the final product is going to be Al2O3. This is very close to that already. It's not exactly. Okay, wait till it gets to 1.99999. Alright, that's it in general.
Peace.
Adios. Now let's talk about combustion analysis. I know you love it. I would pay special attention to combustion analysis. It's gotten the most moans. It's gotten the most complaints. So therefore, I'm going to put a lot of it on the test.
Thank you. Thanks.
Yep.
Bye.
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 Bye. You're an honors cam.
I am.
Okay, the few of the crowd, the honors. Here we go. Okay.
Quick question before we start.
Yeah.
So when we have one of those large problems, since we started with that equation and we went through with it with all those excess and percent yield stuff.
Yeah.
And then for each of the answers, you get a number, and then you're supposed to make that answer into sig things, right?
The very end. That's
Right.
The very end.
But when you keep going, do you use the number that you get with the sig digs from the previous question, or do you use?
If it relies on the previous question, then yes.
Then you can use the one without or with the sig digs.
If there's a question that relies on the answer to the previous question that's been rounded to a sig fig, then you're limited by the lowest amount of sig figs. Right? Yeah. Okay.
All right.
All right. Let me get another problem for you.
Why?
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 Why? Because it's fun.
I have a question. I'm thirsty. Oh.
Okay.
Wait, I have a question.
Yeah.
So in the beginning of this packet, we wrote down the strategy for how to find the limited reactant.
Yeah.
Can you tell me after that how to find the whole excess reactant? I just want to write down this, like, I have like in words.
I can tell you right now what the strategy is.
Yeah, could you?
In words. In words, to find the excess reactant, we're going back to that. That's, okay, so first you find the limiting
So
reactant
what's your
product.
limited, yeah.
So the product in moles from the limiting reactant. Okay, that's what you're going to find first. Right?
Of limiting reactant.
Yeah. And then you change those moles of the limiting reactants product. Okay? It's going to be the product from the limiting reactant, right? You're going to change that into the excess reactants moles. Okay? You change it by the ratio in the reaction. You change it, it's very simple to do that. Then, from there, you change it into the grams of the excess reactant. And that will tell you how much of the excess reactant you used in the experiment. So it's kind of like the amount of gas you've used, you burnt.
I meant something else. Wait, oh, sorry. Okay, I'm sorry. Like here, it's like you wrote like amounts of reactant, like moles of each thing.
Yep, that's what I just told you though.
But it's just
I know.
so product moles of limiting reactant, and then you multiply it by
Okay, so you get the product of moles of limiting reactant, then you multiply it. Then okay, so then you turn it into, you want this like this, then you turn it into the. You want me to tell you in words, or do you want me to do it like this? They're different.
like I'll put it in words like here.
Okay, so from there you turn it into the moles of the excess reactant. I'm just telling you with the words. Moles. You turn the whole thing into moles of excess reactant.
By multiplying?
By multiplying by the ratio in the reaction.
Ratio of reactant.
So it's going to be the ratio of the excess reactant. So the excess reactant moles up here, and you're going to have the product moles down below. Then you're going to do times the grams of the excess reactant. So that's going to be molar mass for the excess reactant. And the mole.
Molar mass?
Yeah. And the mole of the excess reactant. Now, that's going to give you the amount that's actually been used on the experiment.
Right, and then you just subtract the...
Subtract it.
Okay.
Start over. Okay. Let's just do a simple one, alright? A simple one's the easier one. And then from this, the principles that we use in this, you can use in just about any other kind of reaction. So this is something I definitely would recommend you looking over again and again and again to see what the heck I'm really trying to do here. Okay? Alright. So let's try it. So let's say that we start off with, let's say that we have 0.845 grams of this, of CO2, and let's say that we got 0.173 grams of the H2O. Okay? Alright. Now, the strategy here is to figure out how much C we've got in grams, and then find out how much H we've got in grams. Then turn both of those grams of C and the H of C into moles of C and moles of H. Okay? Then from there it turns into an easy empirical formula problem. Very easy. Where you're comparing the moles of the C to the moles of the H. So therefore you can find an empirical formula for C and H. Okay? So that's our strategy. The hardest part is figuring out how much of C there is in CO2 and how much of H there is in H2O. The way you do that is, first, let's do the C part. So you take a 0.845 grams of CO2, and you're going to multiply by this ratio. This ratio is 12.011 over 12.011 plus 15.999 times 2. Okay? This is carbon, this is carbon, and this is O2. So it's the C over the CO2. This gives you the, basically what this is doing is giving you the percent of carbon in carbon dioxide. So if you take this ratio right here and multiply it by the grams of CO2, you're going to get the grams of carbon in CO2, which is what we want. Okay? It's just a trickier start to an empirical formula problem like we did just a few minutes ago. Yeah?
Are we going to learn more about that tomorrow in class?
About this?
Yeah.
I'm just going to